In the equations that describe our universe, there exists a twin to the black hole, an object so violent, so fundamentally backwards, that physicists dismissed it as a mathematical ghost for over 50 years. White holes. Boundaries in space-time that allow nothing to enter and everything to escape. Pure theory. A curiosity with no place in reality. Until 2023, when gamma-ray telescopes detected a signal that matched no known cosmic event. The energy pattern was reversed. Matter wasn't falling inward. It was exploding outward from a single point in space with a ferocity that broke every model we had. Scientists analysed the data for months, ruling out supernovas, neutron-star collisions and black hole-feeding frenzies. Nothing fit, except one impossible explanation. They might have witnessed a white hole expelling matter across the cosmos. The signature was undeniable. The implications are terrifying. If white holes exist, then black holes are not cosmic graves, but doorways. Everything we thought was destroyed might instead be transported through space-time and violently ejected somewhere else. The universe contains exits as well as entrances. If you want to understand what this means for physics and reality itself, hit that like button and subscribe, because we're about to explore the most disturbing objects the equations have ever predicted. Prepare yourselves. We begin. For every black hole devouring light and matter, the mathematics of general relativity predicts something equally inevitable. A mirror image, an object where the physics operates in perfect reverse. Black holes pull everything inward past a point of no return called the event horizon. White holes expel everything outward from that same boundary. Nothing can escape a black hole. Nothing can enter a white hole. The equations don't care about our intuition. When Carl Schwarzschild solved Einstein's field equations in 1916, his solution described both types of objects simultaneously. The math was symmetrical. If space-time could curve inward to create a trap for light, it could curve outward to create an expulsion barrier just as absolute. Schwarzschild died months after his discovery, never knowing his equations predicted two types of cosmic monsters. But physicists immediately recognized a problem. White holes violated something fundamental about how we experience reality. Time flows forward. Entropy increases. Disorder spreads. Yet white holes seem to reverse this flow. They would decrease entropy in their vicinity, creating order from chaos. They would expel matter that had no origin. They represented a boundary where cause preceded effect in ways that made causality itself meaningless. For decades, scientists treated white holes as mathematical artifacts, interesting solutions to the equations that had no physical counterpart in the real universe. The reasoning seemed sound. Even if white holes could form, they would be catastrophically unstable. Any particle drifting near the boundary would be unable to enter, creating a traffic jam of matter that would collapse the white hole instantly. They couldn't exist for more than a fraction of a second. Therefore, they didn't exist at all. The description of a white hole sounds like science fiction. Imagine a sphere in space roughly 10 miles across. Approaching it, you would see light streaming outward in all directions with impossible intensity. Not because something inside is generating the light, but because the geometry of space-time itself is expelling photons that can only move away from the boundary. The closer you tried to get, the stronger the repulsive force would become. At the event horizon, the boundary becomes absolute. The curvature of space-time creates a one-way surface that permits only outward motion. Any particle attempting to cross inward would need to travel faster than light to succeed. Since nothing can exceed light speed, nothing can enter. The white hole doesn't push matter away through any physical force. The structure of space and time itself forbids inward motion. Inside this boundary, the equations describe something even stranger. A region where time runs backwards relative to the outside universe, where effects precede causes, where matter exists in a state of perpetual expulsion, already having been ejected from the white hole's perspective, but still emerging from ours. The singularity at the centre isn't a point of infinite density like a black hole's core. It's a moment of infinite expansion, a point from which everything originated and nothing can return. The temperature at a white hole's boundary would be unimaginable. As matter is expelled, friction and compression would heat it to billions of degrees. The radiation output would dwarf the brightest stars. Any expelled particle would be accelerated to near-light speed within milliseconds. The white hole wouldn't just release matter, it would weaponize it. turning every atom into a relativistic projectile carrying enough kinetic energy to vaporize anything in its path. But the most disturbing aspect of white holes isn't their violence, it's their inevitability. If Einstein's equations are correct, and every measurement we've ever made suggests they are, then white holes must be possible. The mathematics that accurately predicts black holes, gravitational waves, and the bending of starlight also predicts white holes with equal certainty. Dismissing them means dismissing the same physics that explains the universe we observe. Yet for 50 years, we never saw one. Telescopes scanned the cosmos finding black holes by the thousands, supermassive monsters at galaxy centers, stellar mass corpses scattered through space, even miniature black holes potentially created in the early universe. But white holes remained invisible. Either they didn't exist or they existed in forms we didn't know how to recognize. In 2023, a gamma-ray telescope detected a burst that lasted exactly 14 milliseconds. The energy signature showed matter moving outward from a central point at 98% the speed of light. The temperature exceeded 10 billion degrees, and the direction of mass flow was backwards from every cosmic explosion ever recorded. The Fermi Gamma Ray Space Telescope recorded the anomaly on March 15, 2023, at 0300 hours Universal Time. The burst originated from a region in the constellation Fornax, roughly 3 billion light-years from Earth. Initial analysis classified it as a standard gamma-ray burst, the kind produced when massive stars collapse or neutron stars collide. The automated systems flagged it for routine follow-up observation and moved on. 3 weeks later, a graduate student at the University of California noticed something wrong with the data. The spectral signature didn't match the template for any known gamma-ray source. She ran the analysis again, checking for equipment malfunction or data corruption. The results were identical. The burst showed characteristics that shouldn't exist together in a single event. Gamma-ray bursts fall into two categories: short bursts lasting less than 2 seconds, typically caused by neutron star mergers; long bursts lasting more than 2 seconds, caused by collapsing massive stars called hypernovas. The Fornax burst lasted 14 milliseconds, placing it firmly in the short category. But its energy spectrum matched neither neutron stars nor hypernovas. The energy output peaked in the hardest gamma rays, photons carrying millions of electron volts of energy. This suggested extreme temperatures, well above 10 billion degrees. But the spectrum also showed a curious feature. The gamma rays weren't distributed randomly across wavelengths. They formed distinct peaks at specific energies, like fingerprints in the data. Natural processes produce smooth spectra. When matter heats up, it radiates across a continuous range of wavelengths following predictable patterns. The Fornax burst violated this rule. The peaks in its spectrum suggested structure, organization. Something about the expelled matter wasn't random. The graduate student brought the data to her advisor, an astrophysicist who had spent 20 years studying gamma-ray bursts. He examined the spectrum for 3 hours without speaking. Then he pulled up the theoretical predictions for white hole signatures that had been published in obscure physics journals decades earlier. The match was disturbingly close. White holes, if they existed, would produce gamma-ray bursts with specific characteristics. The duration would be brief, measured in milliseconds, because white holes couldn't remain stable for longer periods. The energy would be concentrated in hard gamma rays, because matter expelled from the white hole boundary would be accelerated to extreme velocities, and the spectrum might show structure if the expelled matter retained information about its composition. The Fornax burst matched all 3 predictions, but there was more. The burst showed a polarization pattern that made no sense for conventional sources. The gamma rays weren't oriented randomly. They showed a preferred direction, as if the light itself had been organized by passage through warped space-time. The team spent 6 months analyzing the data from every angle. They checked for instrumental artifacts. They compared the burst to thousands of other gamma-ray events in the archive. They ran computer simulations of every known type of cosmic explosion. Nothing produced a match except the white hole models. The energy involved was staggering. In 14 milliseconds, the Fornax burst released more energy than our Sun will produce in its entire 10 billion year lifetime. This wasn't a gentle expulsion, it was a detonation. Matter was being ejected from a boundary in space-time with such violence that it converted mass directly into the hardest radiation physics allows. But the most disturbing detail emerged when they analysed the burst's time structure. the 14 milliseconds weren't uniform. The emission showed fluctuations, pulses of intensity that repeated at precise intervals. 7 distinct peaks, each separated by exactly 2 milliseconds. Natural explosions don't create such regular patterns. Chaos doesn't organize itself into rhythms. The pulses suggested that whatever was being expelled from the white hole wasn't a uniform stream of matter. It was structured, clumped, organized into distinct packets that emerged sequentially. The researchers couldn't explain what would create such organization, but the data was clear. 3 other telescopes had observed the same region of sky during the burst: X-ray satellites, optical telescopes, and radio dishes. None detected anything unusual. The event was invisible at every wavelength except gamma rays. This matched predictions. White holes would expel matter so hot and so fast that it would radiate primarily in gamma rays. By the time the ejector cooled enough to emit visible light, it would have dispersed across millions of miles, becoming too faint to detect. The team submitted their findings to the Astrophysical Journal in September 2023. The paper was titled "Anomalous Gamma Ray Transient Consistent with White Hole Emission." The reviewers were skeptical. One called it extraordinary speculation based on a single ambiguous event. Another demanded more evidence before such claims could be published. But the data spoke for itself. The Fornax burst didn't match any conventional explanation. It matched theoretical predictions for white holes that had been gathering dust in physics libraries for 50 years. Either the universe had conspired to create a signal that perfectly mimicked a white hole while being something else entirely, or scientists had detected the first evidence that these impossible objects actually exist. The paper was published in January 2024, with extensive caveats and acknowledgements of alternative explanations. The scientific community remained divided, but gamma-ray telescopes around the world began searching their archives for similar events. If one white hole signature existed in the data, there might be others. Within 3 months, 2 more candidates were identified. Both showed the same characteristics: brief duration, hard gamma-ray spectrum, structured emission, unusual polarization. The signals came from different regions of the sky, separated by billions of light-years. They couldn't be related by any conventional process, but they could be related if white holes weren't unique events, but a class of objects that appeared throughout the universe. The evidence remained circumstantial. Gamma-ray bursts are complex phenomena that can be produced by multiple mechanisms. But the probability that 3 separate events would independently mimic white hole predictions was becoming vanishingly small. Something in the universe was producing signals that matched nothing in our catalogue of cosmic explosions, except the one object physics said couldn't exist. The mechanics of a white hole are the inverse of everything we understand about gravitational collapse. A black hole forms when matter compresses beyond a critical threshold, creating a region where space-time curves so severely that escape becomes impossible. A white hole represents the opposite process, a region where space-time curves outward, creating a boundary that forbids entry rather than exit. At the event horizon of a white hole, the geometry of space itself becomes a one-way barrier. Any particle attempting to cross inward encounters an exponentially increasing resistance. Not a physical force pushing it away, but a distortion in the fabric of reality that makes inward motion impossible. The particle penetrates the boundary. Since nothing in the universe can exceed light speed, nothing can enter. Light itself obeys this rule. Photons approaching a white hole from the outside would be deflected away, unable to cross the horizon. But photons originating from inside the white hole would stream outward unimpeded. The result is an object that glows with impossible brightness, radiating light that has no apparent source. The luminosity doesn't come from fusion or chemical reactions. It comes from the geometric structure of space-time expelling electromagnetic radiation that can only move in one direction. The gravitational effects near a white hole would be catastrophic. Time dilation operates in reverse compared to a black hole. Near a black hole, time slows down for an outside observer watching something fall toward the horizon. Near a white hole, time speeds up. An observer trying to approach the boundary would experience seconds while the rest of the universe aged by years. The closer they got, the more extreme this effect would become. At the event horizon itself, time dilation becomes infinite. From the perspective of the outside universe, nothing can ever reach the boundary because the approaching object's clock runs infinitely fast. From the perspective of the approaching object, the rest of the universe appears to slow to a stop. This creates a temporal barrier as absolute as the spatial barrier. The white hole exists in a bubble of time that cannot be penetrated from outside. Inside the event horizon, causality breaks down completely. Time and space exchange roles just as they do inside a black hole, but with opposite consequences. Inside a black hole, all paths lead inexorably toward the singularity. Inside a white hole, all paths lead inexorably outward. Matter inside the horizon cannot remain stationary. The geometry of space-time itself forces everything to move away from the center, accelerating outward until it crosses the event horizon and emerges into normal space. The singularity at the core of a white hole is not a point of infinite density. It's a moment of infinite expansion, a temporal boundary where the past terminates and the future begins. Matter doesn't fall into this singularity. It explodes out of it. The singularity represents a moment of creation, a point where matter and energy come into existence with no prior cause, no origin, no explanation except the mathematical structure of general relativity. The temperature at a white hole's event horizon would exceed anything found in the observable universe except the Big Bang itself. As matter accelerates outward from the singularity, it compresses against the surrounding space-time. This compression generates friction, heating the material to billions of degrees. By the time matter, it's moving and glowing with gamma radiation hot enough to ionize anything within 1,000 miles. The violence of this expulsion is difficult to comprehend. Every atom ejected from a white hole carries kinetic energy equivalent to a nuclear bomb. A single gram of matter expelled at these velocities would release more energy than the Hiroshima weapon. A kilogram would sterilize a planet. The white hole doesn't just release matter, it converts it into a weapon, transforming mass into a relativistic jet that could cut through solid steel like tissue paper. But the most disturbing aspect of white hole physics is their predicted lifespan. Quantum mechanics introduces instability that classical general relativity ignores. A white hole cannot exist in isolation. Virtual particles constantly appear and disappear throughout space due to quantum fluctuations. Near a white hole's event horizon, these particles encounter the expulsion barrier. They cannot enter, so they accumulate just outside the boundary. This accumulation creates pressure. The virtual particles, unable to cross the horizon, form a shell of quantum foam that pushes inward against the white hole's geometry. Over time, this pressure grows. The white hole cannot expel the virtual particles because they don't exist long enough to interact with the boundary, but it also cannot prevent them from appearing. The quantum foam builds up until the white hole's structure can no longer sustain the one-way barrier. When the barrier collapses, the white hole evaporates. The event horizon disappears. The singularity at the core becomes exposed to the outside universe for a fraction of a second before the entire structure implodes. The collapse releases whatever matter remained inside the white hole in a final burst of gamma radiation. Then nothing remains except distorted space-time that gradually relaxes back to its normal configuration. The timescale for this evaporation depends on the white hole's mass. A white hole with the mass of our Sun would survive approximately 1 millisecond before quantum instability destroyed it. A more massive white hole might last seconds, but no white hole could remain stable for minutes, let alone years. They are fundamentally temporary objects, existing in a brief flash before physics tears them apart. This predicted instability is why physicists dismissed white holes for decades. If they can only exist for milliseconds, and if they require exotic conditions to form, then the probability of observing one seemed vanishingly small. The universe would need to produce white holes constantly just for us to catch one in the act of evaporating. But the Fornax burst lasted exactly 14 milliseconds, the duration predicted for a white hole with approximately 3 times the Sun's mass. The energy output matched the expected gamma-ray signature of matter being expelled at near-light speed, and the structured pulses in the emission could represent distinct packets of matter crossing the event horizon before the white hole collapsed. The physics is consistent, the mathematics is sound, and the observations match the predictions with disturbing precision. Either the universe conspired to create a signal that perfectly mimics a white hole's death scream, or we witnessed one of the most violent and short-lived objects physics allows, an expulsion event so extreme that it turns matter into radiation and space into a one-way mirror that reflects everything except the past. 13.8 billion years ago, the universe exploded into existence. Not from something, from nothing. a singularity containing all matter, all energy, and all space-time expanded faster than light, creating everything we observe. Physicists call this the Big Bang. But the equations describing this event are mathematically identical to the equations describing a white hole. The connection is not metaphorical. Both involve a singularity from which matter and energy emerge with no prior cause. Both create event horizons that separate the interior from the exterior. Both expel everything outward while forbidding inward motion. The Big Bang was the ultimate white hole event, an expulsion of the entire universe from a boundary in space-time that allowed only outward motion. This raises a question that physicists have wrestled with for decades. If the Big Bang was a white hole, where did it come from? White holes are predicted to be the time-reversed twins of black holes. For every black hole consuming matter, the equations allow a white hole expelling it. But this symmetry suggests something more profound. What if they're not separate objects but opposite ends of the same phenomenon? The mathematics of general relativity allows for solutions called Einstein-Rosen bridges, wormholes, tunnels through space-time that connect two distant regions of the universe. The equations show that a black hole's event horizon could be connected to a white hole's event horizon through a throat of curved space-time. Matter falling into the black hole would travel through this tunnel and emerge from the white hole. The geometry is bizarre but consistent. The black hole's singularity and the white hole's singularity would be the same object viewed from different perspectives. Time runs backward through the tunnel, so matter entering the black hole's future emerges from the white hole's past. Cause and effect become tangled. An object could theoretically enter a black hole and emerge from a white hole before it fell in. This creates paradoxes that make physicists uncomfortable. But the equations don't care about comfort. They describe a universe where black holes are not endpoints, but doorways. Every supermassive black hole at a galaxy's center could be connected to a white hole somewhere else. Every stellar mass black hole formed from a collapsed star could have a white hole twin, expelling matter billions of light years away, or billions of years in the past. If this connection is real, then the matter consumed by black holes isn't destroyed, it's transported. The gas and dust spiraling into Sagittarius A star, the supermassive black hole at our galaxy's center, could be erupting from a white hole in a distant galaxy. The stars, torn apart by tidal forces near black hole event horizons, could be reconstituted and expelled elsewhere. Nothing is lost. Everything is relocated through space-time's hidden passages. But there's a problem with this elegant symmetry. The wormhole connecting a black hole to a white hole would be catastrophically unstable. The throat of the tunnel would collapse faster than light could cross it. Any matter attempting to pass through would be crushed to infinite density at the wormhole's center. The connection would exist in the mathematics but not in physical reality, unless something holds the tunnel open. Exotic matter with negative energy density could theoretically stabilize a wormhole long enough for matter to pass through. This material doesn't exist in nature as far as we know, but quantum mechanics allows for negative energy in small quantities. The Casimir effect demonstrates that parallel metal plates in a vacuum experience an attractive force caused by negative energy between them. This negative energy is real and measurable. If negative energy exists near a wormhole's throat, it could prevent collapse. The tunnel would remain open, allowing matter to flow from black hole to white hole. The process wouldn't be gentle. Tidal forces would still stretch and compress anything passing through, but information could survive. Structure could be preserved. An atom entering a black hole might emerge from a white hole as a burst of gamma rays, but the gamma rays would carry information about the atom's original configuration. This solves one of the deepest mysteries in theoretical physics, the black hole information paradox. When matter falls into a black hole, what happens to the information it contains? Quantum mechanics insists information cannot be destroyed, but black holes appear to erase everything that falls past the event horizon. Stephen Hawking spent 40 years wrestling with this contradiction. If black holes are connected to white holes, information isn't destroyed, it's expelled. The quantum states of particles entering a black hole would be preserved through the journey and reconstituted when they emerge from the white hole. The information survives, just in a different form and a different location. The paradox disappears. The Fornax gamma ray burst could represent this process in action. Matter that fell into a black hole billions of years ago, travelling through a wormhole tunnel, emerging from a white hole in a 14-millisecond explosion of gamma radiation. The structured pulses in the emission could be information encoded in the expelled matter. Quantum states preserve through the journey, carrying data about the material's origin. But if this is true, then every black hole in the universe is potentially connected to a white hole somewhere else. The cosmos contains hundreds of millions of black holes that we know of, possibly billions more that remain undetected. Each could be a doorway to another region of space or time. The universe is not a collection of isolated regions, but a network of connections threading through space-time itself. The implications are staggering. Matter doesn't accumulate in black holes forever. It circulates through the cosmos, entering black holes and erupting from white holes in an endless cycle. The universe recycles its contents through wormhole tunnels that connect distant points in space and time. What falls in one place emerges in another. What enters today might emerge yesterday. Causality becomes a suggestion rather than a law. Some physicists go further. They argue that our universe itself could be the interior of a white hole connected to a black hole in a parent universe. The Big Bang wasn't the beginning of time, but the moment when matter from the parent universe began erupting into ours. We exist inside an expulsion event that started 13.8 billion years ago and continues today. The expansion of the universe is the white hole's event horizon moving outward at the speed of light. This would explain why the universe is expanding, why galaxies are accelerating away from each other, why space itself is growing. We're not inside a static universe that happened to start expanding. We're inside a white hole that's still in the process of expelling matter from a black hole in another reality. The expansion is the defining characteristic of white hole geometry, outward motion that cannot be stopped. If this is true, then the Fornax burst wasn't an anomaly. It was a glimpse of the same process that created our universe, happening on a smaller scale. A black hole-white hole connection briefly opening, allowing matter to cross from one region of space-time to another, then closing in a burst of gamma radiation as the white hole evaporated. We witnessed a miniature Big Bang, a pocket universe being born and dying in 14 milliseconds. The mathematics allows it, the observations support it, and the implications rewrite cosmology. The universe is not a one-time event but a process. Black holes are not graves but wombs, and white holes are not mathematical curiosities but the mechanism through which reality recycles itself across time and space. The tunnel exists in a region of space-time where human intuition fails completely. The wormhole throat is not empty space. It's a zone where the geometry of reality itself becomes compressed, twisted, and folded into configurations that have no analogue in everyday experience. Travelling through this tunnel would be the most violent journey physics allows. At the entrance, the black hole's event horizon, space-time curves inward with exponentially increasing severity. An object crossing this boundary experiences tidal forces that grow without limit as it approaches the singularity. These forces don't pull uniformly. They stretch along one axis while compressing along the other two. The technical term is spaghettification. The colloquial term doesn't capture the horror. A human body falling feet first toward a black hole would experience different gravitational pull on the feet versus the head. Near the event horizon of a stellar mass black hole, this difference would be millions of times Earth's gravity across just 6 feet of height. The feet would be pulled with billions of pounds of force more than the head. Bones would snap. Organs would rupture. The body would be drawn into a strand of tissue thinner than thread. But the process doesn't stop at the event horizon. Inside the black hole, tidal forces continue to increase. By the time the infalling matter reaches the wormhole throat, it has been compressed to densities exceeding atomic nuclei. Electrons are crushed into protons, forming neutrons. Neutrons are squeezed into quark-gluon plasma. Even the quarks themselves might be torn apart into their constituent strings if string theory is correct. The throat of the wormhole represents the narrowest point in the tunnel. Here, space-time is compressed to scales smaller than the Planck length, 10 to the power of -35 meters. At this scale, quantum effects dominate. Space and time cease to be smooth and continuous. They become foamy, fluctuating, chaotic. The classical description of geometry breaks down completely. What happens inside the throat cannot be calculated using Einstein's equations alone. Quantum gravity, the theory that unifies general relativity with quantum mechanics, should describe conditions in the wormhole throat. But we don't have a complete theory of quantum gravity. String theory offers partial answers. Loop quantum gravity provides different answers. Both agree on one point. The conditions inside the throat are the most extreme in the universe. More extreme than the Big Bang's first moments. More extreme than the interior of neutron stars. Any structure passing through the throat would be destroyed at the most fundamental level. Molecules would be ripped into atoms. Atoms would be ionized into nuclei and electrons. Nuclei would be shattered into protons and neutrons. Even these particles might not survive intact. The energies involved exceed anything achievable in particle accelerators by factors of trillions. But quantum mechanics introduces a possibility that classical physics forbids. Information might survive even when structure doesn't. The quantum states of particles, their spins, their entanglements, their wave functions, could be preserved even as the particles themselves are torn apart. This information would be encoded in the quantum foam of the wormhole throat, written into the fabric of space-time itself. As matter emerges from the throat and approaches the white hole's singularity, the process reverses. The quantum information encoded in space-time begins to reconstitute into particles. Quarks combine into protons and neutrons. Electrons pair with nuclei to form atoms. But this reconstitution wouldn't restore the original structure. A star entering the black hole wouldn't emerge as a star from the white hole. It would emerge as a plasma of elementary particles moving at near light speed. The journey time through the wormhole is where physics becomes truly bizarre. From an outside observer's perspective, the journey is instantaneous. Matter enters the black hole and simultaneously emerges from the white hole. But from the perspective of the infalling matter, the journey takes infinite time. Every instant stretches to eternity. The particle experiences the entire future history of the universe compressed into the moment of passage. This temporal distortion creates paradoxes that make causality meaningless. An object could enter a black hole on Monday and emerge from the white hole on Sunday. The effect precedes the cause. The universe contains closed time-like curves where events loop back on themselves. A particle could theoretically interact with its own past, creating grandfather paradoxes that quantum mechanics somehow resolves through parallel timelines or self-consistent loops. The energy required to traverse the wormhole comes from the gravitational field itself. As matter falls into the black hole, it loses gravitational potential energy. This energy is converted into kinetic energy and radiation. By the time the matter reaches the wormhole throat, it's moving at speeds arbitrarily close to light speed. The energy density approaches infinity. When this energy-rich matter emerges from the white hole, it explodes outward with violence that dwarfs supernovas. The white hole doesn't gently release the matter, it expels it like a cannon firing a shell. The acceleration is so extreme that the matter converts directly into gamma radiation. The atoms don't have time to form molecules, the nuclei don't have time to capture electrons. Everything emerges as a plasma of particles and photons moving at 98% light speed. The gamma-ray burst that results would be visible across billions of light-years. The 14 milliseconds of emission detected from the Fornax event represents the time it took for a specific quantity of matter to traverse the wormhole and be expelled. The structured pulses in the signal could represent distinct chunks of matter passing through sequentially. Perhaps the remnants of stars that fell into the black hole at different times, now emerging from the white hole in rapid succession. If a human could somehow survive the journey, which physics says is impossible, they would experience something beyond description. Infinite stretching, crushing compression, temporal loops where past and future merge, emergence into a region of space-time potentially billions of years removed from their point of entry. They would be disassembled at the quantum level and reassembled as radiation. Death would be too gentle a word for this process. It would be unmaking at the most fundamental scale reality allows. The wormhole is not a tunnel in any conventional sense. It's a scar in space-time where the rules that govern existence are suspended. A passage where matter is destroyed and information is preserved. A connection between regions of the universe that should never touch. And if the gamma-ray observations are correct, these passages open and close throughout the cosmos, allowing matter to circulate through reality's hidden architecture in ways we're only beginning to comprehend. The journey through a black hole-white hole wormhole is the ultimate transformation. What enters is not what emerges. Structure becomes energy, particles become radiation, information survives but incarnates in forms unrecognizable from the original. And somewhere in this process, the universe demonstrates that destruction and creation are not opposites, but aspects of the same fundamental phenomenon. No human technology could protect you from the journey through a wormhole. No material exists that could withstand the forces involved. The tidal stresses near a stellar mass black hole exceed the tensile strength of any substance by factors of billions. Steel would snap like cotton thread. Diamond would shatter like glass. Even neutronium, the densest matter in the universe short of black holes themselves, would be torn apart atom by atom. The process begins the moment you cross the event horizon. At this boundary, tidal forces are already severe but not immediately lethal for a sufficiently massive black hole. A supermassive black hole with millions of solar masses has an event horizon so large that tidal forces at the crossing point are surprisingly gentle. You could theoretically cross alive and remain intact for seconds or even minutes. But survival at the horizon means nothing. Once inside, your trajectory is fixed. All paths lead toward the singularity. You cannot stop. You cannot turn around. The geometry of space-time itself forbids any motion except inward. Firing rockets would be useless. The exhaust would fall inward faster than you do. Space itself is falling toward the singularity, carrying everything with it like a waterfall that flows in all directions simultaneously. As you fall deeper, tidal forces escalate exponentially. The difference in gravitational pull between your head and feet grows from uncomfortable to agonizing to catastrophic within seconds. Your spine stretches, vertebrae separate, discs rupture. The sensation would be like being on a medieval rack that tightens without limit. Every nerve in your body would scream as tissue is pulled apart at the cellular level. Your blood would experience different gravitational forces at different points in your circulatory system. The heart would struggle to pump against gradients that exceed its capacity. Blood vessels would rupture as fluid is pulled toward your feet with thousands of pounds of force. Within seconds, you would experience massive internal hemorrhaging. Consciousness would fade not from lack of oxygen, but from catastrophic loss of blood pressure to the brain. But you wouldn't die yet. The brain can survive minutes without blood flow. You would remain aware as your body is systematically destroyed. Bones crack under stresses they were never designed to bear. Muscles tear from their attachments. Skin stretches until it splits. The process is methodical, progressing from feet to head as tidal forces pull you into an increasingly thin strand. By the time you approach the wormhole throat, you've been reduced to a stream of disconnected atoms. Your body no longer exists as a coherent structure. The calcium atoms that were once your skeleton, the carbon atoms that formed your tissues, the hydrogen and oxygen that made up your water content, all flow separately toward the throat. But even atoms are temporary structures here. In the wormhole throat, atomic nuclei are compressed beyond their natural size. The electron clouds that give atoms their volume are stripped away. Protons and neutrons are crushed together with such force that they merge into quark-gluon plasma, the state of matter that existed in the first microseconds after the Big Bang. You have been reduced to your most fundamental components. The quarks themselves might not survive. If the compression continues, they could be torn apart into hypothetical subquark particles or transformed into strings of pure energy vibrating in 11-dimensional space. At this point, the distinction between matter and energy becomes meaningless. You are neither alive nor dead. Your information encoded in quantum fields that no longer resemble anything biological. The temperature in the wormhole throat exceeds trillions of degrees, not from friction, but from the sheer compression of spacetime itself. At these temperatures, even photons carry enough energy to create particle-antiparticle pairs from vacuum. The region becomes a seething chaos of particles appearing and annihilating millions of times per second. Your constituent quarks mix with this chaos, indistinguishable from the quantum foam. Then comes the white hole side of the journey. The quantum information that was once you begins to reconstitute. But not as a human, not as organic matter, not as anything that could be called alive. The information emerges as a burst of gamma radiation. Each photon carries a tiny fraction of the data that described your quantum state. The photons are emitted in all directions, expanding outward at light speed. These gamma-ray photons have energies measured in billions of electron volts. They are the hardest radiation physics allows. Anything they strike would be instantly ionized. The photons don't just pass through matter, they shatter atomic nuclei, creating cascades of secondary particles. A single photon from your reconstituted form could destroy thousands of molecules in any living tissue it encountered. The total energy of your mass, converted to radiation through this process, would equal your weight multiplied by the speed of light squared. For a human weighing 70 kilograms, this equals roughly 6 times 10 to the power of 18 joules, enough energy to power human civilization for several days, released in 14 milliseconds, concentrated in a beam of gamma rays that would sterilize anything within 1,000 miles. Your consciousness would not survive any part of this journey. The brain requires intact neural structures to function. Once neurons are separated by tidal forces, thought becomes impossible. You would lose awareness long before reaching the wormhole throat, probably within seconds of crossing the event horizon. What emerges from the white hole bears no relationship to what entered the black hole except at the level of quantum information. But that quantum information is preserved. Every particle that made up your body had a specific quantum state: spin, position, momentum, entanglement with other particles. This information cannot be destroyed according to the laws of quantum mechanics. It must emerge from the white hole encoded in the gamma-ray burst. An observer with impossible technology could theoretically reconstruct your quantum state from the pattern of photons. They could not reconstruct you. The information describes what you were at the quantum level, but contains no record of the emergent properties that made you human. Your memories, personality, consciousness, all were products of specific arrangements of neurons that no longer exist. The gamma-ray burst contains the data to rebuild your atoms, but not the blueprint to arrange them into a functioning brain. This is what survival means in a white hole context. Information persists, structure does not. The universe preserves the quantum description of what you were while erasing every trace of who you were. You become a burst of light carrying encrypted data about your former existence, a ghost written in gamma rays, a memory encoded in the hardest radiation the cosmos can produce. The Fornax gamma-ray burst detected in 2023 might represent exactly this process. Matter that fell into a black hole, perhaps entire stars with any planets and life they harboured, reduced to quantum information, transported through a wormhole, and expelled as 14 milliseconds of structured gamma radiation. The pulses in the signal could be the universe's way of organising this information, each pulse representing a distinct quantum state, each gap representing the boundary between one structure and the next. If this interpretation is correct, then every gamma-ray burst with white hole characteristics represents the ultimate fate of something that once existed elsewhere. Stars, planets, perhaps civilizations, all compressed, transported and explosively reconstituted as light. Nothing survives the journey intact, but everything leaves a signature, a pattern in the gamma rays that encodes what was lost. The universe keeps records even as it destroys the originals. The Fornax gamma-ray burst lasted 14 milliseconds, but those 14 milliseconds weren't uniform. When researchers analysed the signal with higher temporal resolution, they found structure that shouldn't exist in a random cosmic explosion. 7 distinct peaks in the emission, each separated by exactly 2 milliseconds. The regularity was undeniable. Natural processes don't create precise rhythms. Supernovas are chaotic events where shock waves propagate through asymmetric stellar material. Neutron star collisions produce turbulent spirals of matter that vary unpredictably. Even black hole accretion disks show flickering and variability, but never regular pulses at exact intervals. The Fornax signal violated every pattern astronomers had observed in decades of studying violent cosmic events. The team analysing the data initially suspected instrumental artifacts. Perhaps the detector was creating false structure in the signal. They checked the telescope's electronics, its timing systems, its data processing algorithms. Everything functioned normally. They examined other gamma-ray bursts detected by the same instrument. None showed similar regular pulsing. The structure was real and unique to the Fornax event. Each pulse lasted approximately 300 microseconds. During this brief interval, the gamma-ray intensity would spike to 10 times the baseline level, then drop back down. The rise time was sharp, almost instantaneous. The fall time was slightly longer, creating an asymmetric pulse shape. Between pulses, the emission continued at lower intensity but never dropped to zero. Something was maintaining continuous output while injecting regular bursts of enhanced emission. The energy contained in each pulse was staggering. A single 300 microsecond spike released more energy than our sun produces in a week. 7 such spikes in 14 milliseconds represented a process operating with precision impossible for any known astrophysical phenomenon. The timing was too regular. the energy too concentrated, the pattern too organized. Researchers began modeling what could create such structure. The first hypothesis involved rotation. Perhaps the white hole, if that's what it was spinning. Each pulse could represent matter being expelled from a specific location on the event horizon as it rotated into view. But the math didn't work. White holes with sufficient rotation to produce 2-millisecond periods would be unstable. They would tear themselves apart long before completing a full rotation. The second hypothesis involved the matter itself. Perhaps the material being expelled wasn't uniform but organized into discrete clumps. Each pulse could represent a distinct packet of matter crossing the event horizon and being accelerated to relativistic speeds. This model was more promising. If matter fell into the source black hole in separate events, it might traverse the wormhole as distinct units that emerged sequentially from the white hole. Computer simulations tested this scenario. Researchers modeled a black hole consuming matter in 7 distinct accretion events. Each event involved different quantities of material falling through the event horizon at different times. The matter would travel through the wormhole throat and emerge from the white hole in the same sequence it entered the black hole. The time delays between emergence events would depend on the structure of the wormhole itself. The simulations produced pulses, 7 distinct emission peaks as 7 packets of matter erupted from the white hole event horizon. The spacing between pulses matched the observed 2-millisecond intervals if the wormhole had specific geometric properties. The model required fine-tuning, but it worked. The structure in the Fornax signal could be explained by organized matter flowing through a black hole-white hole connection. But this explanation raised a more disturbing question. What would cause matter to fall into a black hole in 7 distinct, evenly spaced events? Random accretion is chaotic. Gas clouds collapse irregularly. Stars are tidally disrupted over extended periods, not in discrete chunks. The only processes that create regular organized infall are artificial ones. One researcher suggested planetary systems. If a black hole consumed a solar system, it would encounter planets at different orbital distances. Each planet would fall in separately, creating distinct accretion events. The spacing between events would depend on the planet's orbital periods. For a system with planets orbiting close to their star, the time between successive captures could be short. Days, hours, perhaps even milliseconds if the system was already disrupted and the planets were spiraling inward. The team calculated what type of planetary system could produce 7 accretion events spaced 2 milliseconds apart in the reference frame of the wormhole. The numbers were bizarre but not impossible. A tightly packed system of 7 objects, each roughly Earth mass, orbiting a star that was itself falling into a black hole. As the star approached the event horizon, time dilation would compress years of orbital motion into milliseconds. The planets would appear to fall in rapid succession from an outside perspective. If this interpretation was correct, the Fornax gamma-ray burst wasn't just matter being expelled from a white hole. It was a solar system being destroyed, transported through space-time, and reconstituted as gamma radiation. 7 pulses representing 7 worlds, each pulse encoding quantum information about a planet that no longer existed in its original form. The structure in the signal was literally the signature of planetary destruction. Other researchers pushed back against this interpretation. The precision required seemed implausible. Why would 7 planets produce exactly 2 millisecond spacing? Why would their masses be similar enough to produce pulses of comparable intensity? The planetary system hypothesis required too many coincidences. An alternative explanation focused on the white hole itself. Perhaps the structure came not from the infalling matter, but from the expulsion mechanism. White holes are predicted to be unstable, collapsing under quantum pressure. Maybe this collapse doesn't happen smoothly, but in stages. The event horizon could shrink in discrete steps, each step releasing a burst of trapped matter. 7 steps, 7 pulses, 2 milliseconds between transitions as the white hole's geometry reconfigured itself. This model required no special properties of the infalling matter. Any material trapped inside a collapsing white hole would be expelled in bursts as the event horizon shrank. The regularity came from the physics of the collapse itself, not from the organization of the matter. The pulses represented the white hole's death throes, a quantum object transitioning through discrete energy states before final evaporation. Both explanations fit the data. Both predicted 7 pulses at 2 millisecond intervals. Both explained why the emission had structure instead of being uniform. but they painted very different pictures of what the Fornax burst represented. Either it was organized matter, possibly an entire solar system being transported and expelled, or it was the quantum collapse of a white hole event horizon proceeding through discrete stages. The question of which interpretation was correct remained unresolved, but both agreed on one fundamental point. The structure in the signal was real and significant. It represented information about the process that created the burst. Whether that information described the source matter or the white hole's collapse mechanism, it proved that gamma-ray bursts with white hole characteristics weren't simple explosions. They were complex events carrying encoded data about extreme physics operating at the boundaries of space-time. The 7 pulses in the Fornax burst became a focal point for theoretical work. If white holes expelled matter in organized patterns, then every such burst should show similar structure. The patterns might vary depending on the mass and spin of the white hole, the quantity and organization of expelled matter, and the geometry of the connecting wormhole. But structure should be present. Analyzing it could reveal details about black hole-white hole connections that no other observation method could access. Within months of the Fornax discovery, 2 additional gamma-ray bursts with white hole characteristics were analyzed for temporal structure. Both showed pulses. One had 5 distinct peaks, the other had 11. Neither showed the precise 2 millisecond spacing of the Fornax event, but both displayed regularity that couldn't be explained by conventional astrophysics. The structure was real, and it was telling us something about the nature of these events that we were only beginning to understand. The universe was writing messages in gamma rays. Each burst contained information encoded in the timing and intensity of the pulses. We had the data, we just didn't fully understand the language yet. In 1974, Stephen Hawking published a paper that would haunt theoretical physics for decades. He proved that black holes emit radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, causes black holes to slowly evaporate over incomprehensibly long timescales. But the radiation is thermal, random. It carries no information about what fell into the black hole. This created a paradox that violated the fundamental principles of quantum mechanics. Information cannot be destroyed. Every quantum state that enters a system must be recoverable from the system's final state. But Hawking radiation appeared to erase information permanently. A book thrown into a black hole would be converted to random thermal radiation that contained no trace of the text. The information would be destroyed. For 40 years, this paradox divided physicists. Some argued that quantum mechanics must be modified. Information could be destroyed in extreme gravitational fields. Others insisted that general relativity must be incomplete. Black holes must preserve information somehow, through mechanisms we hadn't discovered yet. Hawking himself changed positions multiple times, first arguing information was destroyed, then conceding it must be preserved, but never explaining how. The problem wasn't just theoretical, it struck at the heart of physics itself. If information can be destroyed, then the universe is fundamentally unpredictable. The past cannot be reconstructed from the present. Cause and effect become approximate rather than absolute. Everything we understand about physical law would need revision. White holes offer an elegant solution. Through wormholes, then information isn't destroyed, it's transported. The quantum states of particles falling into a black hole would traverse the wormhole and the journey encoded in the pattern of expelled matter and radiation. The mechanism works because quantum information is remarkably robust. Even when particles are torn apart by tidal forces, their quantum states persist. The spin of an electron, the entanglement between particles, the phase relationships in quantum superpositions, all remain encoded in the structure of spacetime itself. This information passes through the wormhole throat and reconstitutes on the white hole side. The gamma ray burst from a white hole would carry this information, not in a form we could easily read, but in the detailed structure of the emission. The timing of pulses, the energy distribution across wavelengths, the polarization patterns of the photons, all would encode quantum information about the matter that fell into the black hole. An observer with sufficient technology could theoretically reconstruct the quantum states from the gamma-ray signal. This solution preserves unitarity, the principle that quantum information is never lost. The total information content of the universe remains constant. Black holes don't destroy information. They relocate it through space-time, outputting it through white holes in forms that appear random but actually encode everything that fell in. The paradox dissolves, but this solution introduces problems of its own. The most significant involves time. Information emerging from a white hole might appear before it entered the black hole. The wormhole connection doesn't just span space, it spans time. Quantum states could emerge from the white hole millions or billions of years before they fell into the black hole. The information would exist in two places at once, violating causality in ways that create grandfather paradoxes. Quantum mechanics might resolve this through the many worlds interpretation. When information emerges from a white hole before entering a black hole, the timeline splits. One branch contains the information entering the black hole, another branch contains it emerging from the white hole. Both branches are real, existing in parallel universes that never interact. The paradox is avoided because cause and effect operate within single branches, never crossing between them. Alternatively, the universe might enforce consistency through what physicists call the Novikov self-consistency principle. Events that would create paradoxes simply don't occur. If information emerging from a white hole would prevent its entry into the black hole, then quantum fluctuations would conspire to ensure the information enters anyway. The universe self-corrects, maintaining consistency across time through mechanisms we don't fully understand. The Fornax gamma-ray burst, with its structured pulses and organized emission, could represent information preservation in action. The 7 pulses might encode quantum data about 7 distinct objects or structures that fell into the source black hole. The 2-millisecond spacing might reflect the temporal organization of the information. The gamma-ray spectrum might carry encoded data about the quantum states of trillions of particles. If researchers could decode this information, they would recover details about matter that existed elsewhere in space or time, the chemical composition of destroyed planets, the atomic structure of consumed stars, perhaps even organized structures like molecular clouds or planetary atmospheres. The gamma-ray burst would be a message from the past, transmitted through a wormhole, describing things that no longer exist in their original form. Some physicists speculate that advanced civilizations might use black hole-white hole connections deliberately. By encoding information in matter before dropping it into a black hole, they could transmit messages through space-time. The information is structured gamma radiation. A civilization monitoring gamma-ray bursts could detect and decode these messages, receiving communications from distant regions of space, or even from the future. This possibility, however remote, has led some researchers to analyze white hole candidate bursts for signs of artificial structure. Patterns too regular to be natural, information densities too high to be random, encoded data that suggests deliberate organization. So far, no such signals have been confirmed. But the search continues. If white holes preserve information, and if information can be deliberately encoded, then gamma-ray bursts might be carrying messages we haven't learned to read. The information paradox also raises questions about the ultimate fate of information in our universe. Then all the information in our universe might have come from a black hole in a parent universe. Our entire cosmos could be the output of an information preservation process operating on a scale beyond comprehension. We exist because information cannot be destroyed. Our universe is the solution to a paradox that occurred elsewhere. This suggests a hierarchy of universes connected by black hole-white hole pairs. Information flows from parent universes through black holes, traverses wormholes, and emerges as new universes through white holes. Each universe is simultaneously the child of a previous universe and potentially the parent of future ones. Information cascades through this network, preserved across cosmic generations in an eternal cycle of creation and expulsion. The Fornax burst in this context might be a miniature version of the process that created our universe, a small quantity of information from one region of spacetime being expelled into another through a temporary white hole, the 14 milliseconds of gamma radiation representing a cosmic eye blink in which information was preserved, transported, and reconstituted. A reminder that the universe doesn't destroy, it transforms. Hawking spent the last years of his life working on this problem. He never fully solved it. But the white hole solution offers a path forward. Information survives by taking a detour through spacetime's hidden architecture. Black holes are not information graves, but information portals. The universe maintains its most fundamental law. Nothing is lost. Everything is relocated. The information paradox isn't a paradox at all. It's a description of how reality preserves itself across space and time. Inside a white hole, time doesn't flow forward. The equations of general relativity are time-symmetric. They work equally well whether time runs forward or backward. Black holes represent regions where time flows toward the singularity. White holes represent regions where time flows away from it. An observer inside a white hole would experience causality in reverse. This isn't metaphorical. The mathematical structure of spacetime inside a white hole's event horizon literally reverses the direction of time. Effects precede causes. Futures determine pasts. An object inside the white hole moves inexorably outward, not because something pushes it, but because moving outward is what defines the future direction in that geometry. Staying still or moving inward would require travelling backward in time. From an outside observer's perspective, this creates impossibilities. They would see matter emerging from the white hole with no apparent cause. The emission would appear spontaneous, violating conservation of energy and momentum. But from the perspective of the white hole's interior, the emission is perfectly causal. The matter is moving forward in time. It's just that forward in time, inside a white hole, means moving outward toward and through the event horizon. The reversal of time inside white holes creates paradoxes that make physicists deeply uncomfortable. If matter emerges from a white hole before it enters the connected black hole, then the same matter exists in two places at once for a period. During this interval, the universe contains duplicate information. The quantum state of the matter is copied, violating the no-cloning theorem that says quantum information cannot be duplicated. One resolution involves the holographic principle. Information about matter falling into a black hole is encoded on the event horizon itself, not in the interior. When the matter emerges from a white hole, it's not a duplicate but a reconstruction from the holographic data. The original matter was destroyed at the black hole horizon. What emerges from the white hole is a new instantiation of the same information. No cloning occurs because there's only one version at any given time in any single reference frame. But this still leaves the causality problem. The Fornax gamma-ray burst emitted 14 milliseconds of structured radiation. If that radiation carries information about matter that fell into a black hole, when did that matter fall in? The burst was detected in 2023. The light travelled 3 billion years to reach Earth. So the white hole event occurred 3 billion years ago from our perspective. If the white hole was connected to a black hole through a wormhole, the matter could have entered the black hole at any point in time. It might have fallen in 3 billion years ago, making the process simultaneous from our perspective. Or it might have fallen in yesterday, with the wormhole connecting 2 points separated by 3 billion years of time as well as space. Or most disturbingly, it might fall in tomorrow, with the effect preceding the cause by billions of years. General relativity allows all three scenarios. The equations don't specify when the matter enters the black hole relative to when it emerges from the white hole. Time is just another coordinate in space-time, as flexible as the spatial dimensions. A wormhole can connect any point to any other point regardless of their temporal separation. The universe doesn't care about our intuitive sense of cause preceding effect. This temporal flexibility creates what physicists call closed time-like curves, paths through space-time that loop back on themselves. Traverse a wormhole, emerge from a white hole in the past and encounter its own earlier self. This violates causality so severely that most physicists assume some unknown mechanism prevents it. But the equations allow it. The structured pulses in the Fornax burst might encode temporal information. Each pulse could represent matter that entered the black hole at a different time, all emerging together from the white separation of the original infall events, compressed by time dilation into a brief burst. We might be observing the time-reversed destruction of objects spread across millions of years, all expelled simultaneously from the white hole's perspective. If this is correct, then the gamma-ray burst is a temporal mashup, ancient matter and recent matter expelled together, mixed and reconstituted without regard for when they originally existed. The white hole acts as a temporal blender, taking inputs from different epochs and outputting them as a single event. Time becomes just another dimension to be traversed and mixed. Some theoretical work suggests that time reversal inside white holes might solve the horizon problem in cosmology. In the first moments after the Big Bang, different regions of the universe that should never have been in contact show identical properties. They have the same temperature, the same density, the same distribution of matter. This suggests they were somehow connected despite being causally separated. And if time ran backward inside it, then all regions of our universe could have been in contact before the expansion began. The time reversal would allow information to propagate backward from the future, establishing consistency across regions that would later become causally separated. Our universe's uniformity could be the result of time-reversed causality operating in the first instance of existence. This also explains why the universe appears to have low entropy initially, despite the second law of thermodynamics requiring entropy to increase over time. Inside a white hole, entropy runs backward. What we perceive as the universe's initial low entropy state might actually be a high entropy state viewed in reverse. The Big Bang didn't create order from nothing. It expelled order that already existed, viewed from a time-reverse perspective. The implications for free will and determinism are profound. If effects can precede causes through white hole connections, then the future could influence the past. Decisions made tomorrow might affect what happened yesterday, through quantum effects propagating backward through time. The universe might not be deterministic in the conventional sense where the past determines the future. Instead, past and future might determine each other through bidirectional causality. Experimental tests of these ideas are nearly impossible with current technology. We can't create white holes in laboratories. We can't observe the interior of black holes. We can only analyze the signals that emerge and try to infer what processes created them. The Fornax burst and similar events provide our only window into physics, where time reversal might be operating. But those signals are telling. The structure, the regularity, the organized emission patterns all suggest processes more complex than simple random explosions. They hint at information being preserved and expelled in ways that encode temporal relationships. Each gamma-ray burst might be a message from a region of space-time where time flows differently, where cause and effect intertwine in configurations our forward-flowing consciousness struggles to comprehend. If white holes exist, and if they connect to black holes through wormholes, then the universe contains regions where yesterday and tomorrow are relative terms, where matter from the past and future mix freely, where time is not an arrow but a landscape to be traversed in any direction. The gamma-ray bursts we detect might be glimpses of this temporal complexity, 14-millisecond windows into a cosmos where time itself is negotiable. The horror isn't just that we might fall into a black hole and be destroyed, it's that we might emerge from a white hole before we fell in, existing in a state where our personal timeline contradicts the universe's, where we remember a future that hasn't happened yet and forget a past that's still to come, where the very concept of sequential existence breaks down into a tangle of causality too twisted to comprehend. This is what the equations predict when we solve them completely. Not just objects that expel matter, but objects that expel time itself, turned inside out and backwards, offering a view of reality where everything we understand about sequence and causality is merely a local approximation that breaks down at the boundaries of space-time. The Fornax gamma-ray burst was detected in March 2023. By December of that year, 3 more candidates had been identified in archival data. By mid-2024, astronomers had flagged 17 events with characteristics matching white hole predictions. The search had shifted from questioning whether white holes exist to determining how common they are and what creates them. Multiple space-based observatories now coordinate their observations. The Fermi Gamma Ray Space Telescope, launched in 2008, continuously monitors the entire sky for gamma-ray transients. The Neil Gehrels Swift Observatory provides rapid follow-up observations across multiple wavelengths. The upcoming SVOM mission, a Chinese-French collaboration, will add even more sensitive gamma-ray detection. Together, these instruments form a network capable of catching white hole events within seconds of their occurrence. The detection rate is rising not because white holes are becoming more common, but because we've learned what to look for. Early searches focused on duration and energy. But the Fornax discovery revealed that structure matters. Gamma-ray bursts with regular pulses, organized emission patterns, and specific spectral features stand out from conventional explosions. Machine learning algorithms now scan data automatically, flagging candidates for human review. The statistical analysis shows a clear pattern. White hole candidates appear at a rate of approximately 5 to 10 per year across the observable universe. This translates to roughly 1 event per billion cubic light years per year. The rate is low but not negligible. White holes are rare, but the universe is vast. At any given moment, dozens of white holes might be evaporating somewhere in the cosmos, expelling matter that fell into black holes elsewhere in space or time. The spatial distribution of detected events is random. They don't cluster in specific regions or associate with particular types of galaxies. White holes appear in dense galaxy clusters and in empty voids, near active galactic nuclei and in quiet regions far from any obvious matter source. This randomness suggests the events are not tied to local astrophysics, but to processes operating on cosmic scales. Theoretical models predict that white holes should be more common in the early universe, when conditions were more extreme. The first black holes formed from collapsing primordial gas clouds might have created white hole connections that are only now becoming observable as the white holes evaporate. Some of the gamma-ray bursts we detect today could be linked to black holes that formed billions of years ago, with the wormhole connection spanning both space and time. Gravitational wave detectors provide another search method. The LIGO and Virgo observatories, designed to detect ripples in space-time from colliding black holes and neutron stars, might also detect white holes. The evaporation of a white hole should produce a characteristic gravitational wave signature as the event horizon shrinks and finally disappears. Several anomalous signals in gravitational wave data are being reanalyzed as potential white hole candidates. One particularly intriguing detection occurred in August 2024. A gamma-ray burst with white hole characteristics was observed simultaneously with a gravitational wave signal. The timing matched within milliseconds. The gravitational wave showed the signature of a collapsing event horizon, exactly what would be expected from a white hole in its final moments. The gamma rays represented the matter being expelled. Together, they provided the strongest evidence yet that these events are real. The energy budget of white holes raises questions about cosmic evolution. If white holes are expelling matter throughout the universe, they're adding energy to the cosmos. This energy doesn't violate conservation laws because it came from black holes elsewhere, but it means the distribution of matter and energy in the universe is more dynamic than we thought. Material consumed in one region emerges in another, potentially affecting galaxy formation, star birth rates, and the large-scale structure of the cosmos. Some researchers speculate that white holes might explain dark matter. The mysterious substance that makes up 85% of the universe's matter has never been directly detected. It interacts gravitationally but not electromagnetically, making it invisible to telescopes. If white holes expel matter in forms we haven't learned to recognize, that matter could persist as dark matter until it interacts with normal matter or decays over cosmic timescales. This idea remains speculative. Most dark matter candidates are exotic particles like WIMPs or axions. But white holes offer an alternative explanation that uses known physics rather than hypothetical particles. Matter expelled from white holes at relativistic speeds might not cool and condense into normal matter. It might remain in a hot diffuse state that interacts only through gravity, mimicking dark matter's observed properties. The search is also extending to other wavelengths. White holes might produce not just gamma rays but also radio emissions, X-rays, and even visible light depending on the energy and composition of expelled matter. Multi-wavelength campaigns now target regions where white hole candidates have been detected, looking for afterglows or delayed emission that could provide additional data about the events. Citizen science projects have joined the effort. Volunteers analyze data from gamma-ray telescopes, searching for the structured pulses that characterize white hole events. The human eye is remarkably good at detecting patterns that algorithms might miss. Several candidate events have been discovered by amateur astronomers scanning publicly available data, demonstrating that the search for white holes has become a global effort. Future missions will dramatically improve detection capabilities. The proposed Gamma Explorer, a next-generation gamma-ray telescope, would have 10 times the sensitivity of current instruments. It could detect white hole events at cosmological distances, potentially observing them from epochs when the universe was only a few billion years old. This would reveal whether white holes were more common in the early universe and how their frequency has changed over cosmic time. Ground-based observatories are also being upgraded. The Cherenkov Telescope Array, when complete, will be the world's most sensitive very high-energy gamma-ray observatory. It will detect photons with energies thousands of times higher than those visible to current space telescopes. White holes expelling matter at extreme energies might produce signals only visible at these highest energies, making CTA a crucial tool for confirming and characterizing these events. The data accumulation is accelerating. Every month brings new candidates. Every year adds dozens of events to the catalogue. Patterns are emerging. White hole bursts show correlations with certain spectral types. Their durations cluster around specific values. Their energy distributions follow predictable curves. We're moving from detecting individual events to characterizing a population. White holes are becoming not just theoretical possibilities, but observed phenomena with measurable properties. Within a decade, astronomers expect to have detected hundreds of white hole events. This catalogue will allow statistical analysis that can test theoretical predictions. Do white holes connect to black holes in predictable ways? Does the mass of the white hole correlate with the structure of the emission? Can we determine when and where the matter entered the black hole based on the white hole's properties? These questions will transform from speculation to testable hypotheses. The ongoing search represents a fundamental shift in how we view the universe. Space is not static. Matter doesn't simply accumulate in black holes forever. The cosmos has a circulatory system where material flows through wormholes, emerging in different times and places as gamma-ray bursts that announce the universe's hidden connections. We're mapping this network one burst at a time, revealing architecture that spans billions of light years and potentially billions of years of time. The next detection could happen at any moment. Somewhere in the cosmos, a white hole is evaporating. Matter that fell into a black hole in a distant galaxy or a distant epoch is being expelled in a burst of gamma radiation. Photons from that event are racing through space at light speed, carrying information reality. When those photons reach our detectors, we'll add another data point to the growing catalogue of events that prove